Hello student, welcome to my channel IIT Forum. Myself Parth Chaudhary. So today's lecture is basically based on the hydrogen bonding. So as I discussed in my previous lecture about the type of bonding, so there was a strong bonding and weak bonding. So I have discussed about this intermolecular force of attraction in my last video. So if you have seen this video, so you know about it. So I have discussed about van der Waals force of attraction. So there was a three type of bond of attraction, force of attraction. So there was a dipole attraction. So there was a dipole induced dipole attraction, and there was a induced dipole attraction. So as we named as a name of the scientist of this bonding, so in dipole interaction is known as a Kissen force, right? And dipole induced dipole attraction is known by this dy force, right? And this induced dipole attraction is known by a London force. So that I had discussed in the last video. So I was discuss also about this dissociation energy, means how much energy you need to break this type of bond, right? So today's lecture I want to discuss about this hydrogen bonding, because you have a clear idea about this type of bonding, which are strong and which are weak type of bonding. So if you have idea about this dissociation energy, so you will have a clear idea about it. Okay, so in my last video, if you see, so in first I have to write this ionic lattice, that is ionic bonding. Another was this covalent bonding, right? There's a covalent bond. Another was a hydrogen bond that I will discuss in this video. This hydrogen bonding. Another was a London dispersion. Okay, London dispersion force, that is a induced dipole bond. Okay, so as you know, the dissociation energy, so in this column it is a dissociation energy. So in ionic lattice, the dissociation energy is about 1100 to 20,000. Okay, it's the unit is a kilojoule per mole. Okay, kilojoule per mole. So this is a unit. So this is a ionic lattice, that so you need 1100 to 20,000 energy to break this ionic lattice. But in covalent lattice you need 130 to 1100 kilojoule per mole. But in hydrogen bonding is a very less, it's about 4 to 50 kilojoule per mole. Okay, 50 kilojoule per mole. And is a London dispersion is a very weak force of attraction, so you need less than 4 kilojoule per mole. So I think you have a clear idea about this dissociation energy, so you can say which bond is strong and which bond is weak, right? So in this video I'll discuss about hydrogen bonding. So guys, do you know what is hydrogen bonding? The hydrogen bonding is maybe defined as a weak electrostatic force. So as you know this, you can see here, because the electrostatic force of attraction is weak, because we need 4 to 50 kilojoule per mole energy to break this hydrogen bonding, right? So it's a weak electrostatic force of attraction that operate between hydrogen atom that is covalently bonded to atom of high electronegativity. Okay, so hydrogen atom which is covalently bonded with some X, like X means should be a high electronegative atom. So if you have seen my videos on dipole moment, so you have a clear idea about this. So if this hydrogen is bonded with some X which is high electronegative atom, so there is a generation of partial charge, right? Because since what is covalent bond means hydrogen share one electron and this X share one electron, right? So if X is more electronegative, this sharing, that is a covalent sharing electron pair will move toward X, that is high electronegative atom. So there is a generation of partial charge, their generation of partial charge. So X is more electronegative, so this pair of electrons move toward X, so it form a delta negative charge, and this hydrogen will have a delta positive charge. So this is, this is the difference between charge, because of this electronegativity of atom. So guys, the energy of such bond varies from 5 to 10 kilocalorie per mole. So as I discuss in my discuss here is about 4 to 50, the hydrogen bond dissociation energy. So you need 4 to 5 kilocalorie per mole, okay, to break this bond, right? So what type of X we can consider? X is a high electronegative atom. So here generally fluorine, oxygen and nitrogen, okay. So if hydrogen is covalently bonded with such atoms, right, fluorine, oxygen and nitrogen, so there is a generation of partial positive and negative charge on this, right? So the covalent bond between this hydrogen and electronegative atom is considerably polar. You're right, because the electronegative atom attracts this bonding electron toward itself. So there is a bonding electron, it is attracted toward this self. So that is why this X has a delta negative charge and the hydrogen has a delta positive charge. So this partial positive charge develop this hydrogen, and the partial negative charge developed on the X, that is high electronegative atom. So now this what is this hydrogen bonding? This hydrogen bonding means there is a hydrogen, there is a X, like whatever it is, it's maybe fluorine, it's maybe oxygen, or it's maybe nitrogen, okay. So guys, in there is a lot of molecule, right? So if the neighbor molecule is the same, like H and X, so here this X is same, this X may be fluorine, maybe oxygen and maybe nitrogen. So here is a delta negative and delta positive charge. So here also is a delta positive and delta negative charge, okay. So guys, here these negative and positive, this X negative and positive will form a bond because of electrostatic, that is delta negative and delta positive. So guys, this is known as a hydrogen bonding generally. So it is a generally, you can say hydrogen bonding is a special type of dipole-dipole interaction, right? The dipolar hydrogen fluoride molecule, if you take X as a fluoride, so is the dipolar hydrogen fluoride molecule, for example, is held together by hydrogen bonding. So it's look like this hydrogen and this fluoride, and here is hydrogen and here is fluoride. So it will bond like this, is called a hydrogen bonding, right? Is a very weak electrostatic force of attraction, but yeah, it is relatively higher than this London dispersion force or Van der Waals force of attraction, because the dissociation energy diagram. So hydrogen bonding needs 4 to 50 kilojoule per mole, but only less than 4 kilojoule per mole is needed to break this Van der Waals type of bonding. So I think you have a clear idea about it, right? So guys, there is something more about I have to discuss, because this hydrogen bonding has a two type of hydrogen bonding. So this hydrogen bonding is two type of hydrogen bonding, one is guys intramolecular, and another is a intermolecular. Okay guys, I think you don't have any problem here. So I'll discuss individually what is intramolecular and what is intermolecular hydrogen bonding. So first I'll discuss intramolecular hydrogen bonding. So the name intra means between the same molecule. Like let me take an example first. So this is a benzene ring, right? So if you have a OH group here, and if you have a C double bond OH group here, okay, so that is this a molecule. So here is there any hydrogen bonding possible? First ask yourself. So first what you have to do, you have to keep the concept of hydrogen bonding. So here hydrogen and oxygen is covalently bonding, right? So hydrogen is delta positive and oxygen is delta negative. In this structure also, here hydrogen and oxygen is covalently bonded. So here is delta negative and delta positive. So guys, this oxygen is can bond it here, and this oxygen can bond it with this hydrogen. So guys, here the hydrogen bonding is possible. So, and this is a intramolecular hydrogen bonding. Why? Because you know, the same molecule, in the same molecule the hydrogen bonding has occurred, so that is why it is known as intramolecular hydrogen bonding. But you know, as I discussed one example before, like hydrogen fluoride, right? So in hydrogen fluoride itself, it's a molecule, so so intramolecular is not possible here because only hydrogen and fluoride is here. So it's a covalent bond, right? Hydrogen and fluoride. So but hydrogen bonding is possible with the neighbor atom, right? With the neighbor hydrogen and fluoride atom. So intermolecular concept is the bonding between neighbor molecule. Okay, it's a neighbor molecule, the hydrogen fluoride and another hydrogen fluoride, but here you can see the same molecule has a hydrogen bonding. So as we that is why we call it as a intramolecular hydrogen bonding, but here we call is a intermolecular. You know, this inter term means with a neighbor molecule. This is intermolecular hydrogen bonding. So I think you have a clear idea about this intramolecular and intermolecular hydrogen bonding. So there is a lot of example. I just gave you this example to better understand about this concept. Okay, so guys, why do we need to study this hydrogen bonding? So why the importance of this hydrogen bonding? So you know guys, so there is a in the different application of hydrogen bonding. So if you know this melting point, this physical property actually is a melting point, boiling point, solubility. So hydrogen bonding will have a great importance in such a property. So like if I give you some example, like you have a container. Okay, so you have a solvent water, right? So now if you put two solvent here, okay, or two different molecules here, like you take a benzene and another is acetone. Okay, so we have a two type of solvent, one is benzene and another is acetone. So like if I take benzene as 1 and acetone as a 2, so first ask yourself which one will be soluble into water, because both acetone and benzene is a organic solvent and water is a universal solvent and is a inorganic solvent, you can say, right? So you have two options. One is option A, if you put benzene into water, is it soluble, and second is if you put acetone into water, which are soluble. So which one will be soluble, benzene or acetone? So here the hydrogen bonding will play a very important role. How? If you took this H2O, right, if you break down H2O into this structure, so you know oxygen has a lone pair, right? Now benzene, okay, so benzene. So what is the concept of hydrogen bonding, guys? The concept of hydrogen bonding means, so you have to be a electronegative atom and hydrogen is covalently bond. So here hydrogen is delta positive, oxygen is delta negative, and hydrogen and oxygen is covalently bond. So you know, in water there are a lot of hydrogen bonding between water molecules, but if you put another molecule like benzene, so you can see what is actually benzene, C, so it is look like this, right? So you know, there is a condition between hydrogen bonding, so you have to be hydrogen have to be a covalently bonded with fluorine or oxygen or nitrogen. So carbon was not there in the list, so that is why in benzene hydrogen bonding is not possible. So here not possible in benzene into benzene, as well as benzene with water molecule. That is why benzene will not soluble into water. So one is a organic, one is a inorganic. Okay, so it will not be soluble into water. But if we take example of the acetone, okay, take example of acetone. So here H2O, right, hydrogen and oxygen here is a covalently bonded, so hydrogen is less electronegative, so it's a delta positive, and oxygen is more electronegative, it's a delta negative. Okay, but you see this acetone, what is the structure of acetone is CH3, So here oxygen, right, you know oxygen, so this oxygen is a delta negative, so this oxygen will form a hydrogen bonding with this hydrogen. So that is why acetone is an organic solvent, but it will soluble into water because it form a hydrogen bonding into water. So if you put this water, if you have a water and you put acetone here, if you put acetone here, so it will soluble, it will soluble. Why? Because it form a hydrogen bonding, it form a hydrogen bonding with water. That is the same is happen with alcohol also. So this is the importance of hydrogen bonding, as well as some another question will be the boiling point. So why water has a boiling point of 100, right? This is 100 degrees centigrade, but this hydrocarbon has less, this hydrocarbon has less. Why? Because water form a hydrogen bond between itself, between its intermolecular hydrogen bond in water molecule, but in hydrocarbon there is not have any hydrogen bonding, so it has a van der Waals type of bonding, van der Waals type of bonding. So as you know the dissociation energy list, so hydrogen bonding needs 4 to 50 kilojoule per mole to break this hydrogen bonding. So that is why this hydrogen bonding is much stronger bonding as compared to hydrocarbon. So hydrocarbon is generally less than 4 kilojoule per mole. So that is why it differ the boiling point. What is boiling point? Means you have to break these intermolecular forces, right? So boiling point is doesn't mean that you need to break this covalent bond. It means you have to break these two H2O molecule that is attracted to each other by hydrogen bonding. So you need to break this hydrogen bonding. So that is why its hydrogen bonding is much stronger as compared to van der Waals bond. So we need 100 degree to make it boil, right? And this hydrocarbon we need a less temperature. Even at room temperature this hydrocarbon is volatile, so that is why this boiling point is very low. So this is the importance of hydrogen bonding. So guys, I think you have a clear idea about this hydrogen bonding. So this video is based on this hydrogen bonding, so I think you have idea. So thank you, that's it, we'll see in my next video. Thank you.